Greed is good. This paper explores the role of exploration and exploitation in Bayesian optimization and introduces a new epsilon greedy algorithm, which is at least as effective as the state of the art. Bayesian optimization is used for the optimization of expensive to evaluate functions. It constructs a probabilistic model of the function being optimized, and this gives a measure of uncertainty in the prediction, which allows exploration of potentially promising regions to be balanced with the exploitation of known good regions. The balance between exploration and exploitation is determined by the acquisition function, which can be cheaply maximized by, for example, an evolutionary algorithm to find the next point to be expensively evaluated. The evaluated point is then used to augment the training data for the next iteration. Gaussian processes are commonly used as surrogate models as they provide natural estimates of the prediction uncertainty. Here, the dashed line shows the true function to be maximized, the green line shows the mean prediction, and the light green shading shows two standard deviations around the mean. And there's large uncertainty away from the evaluated points marked in blue. After maximizing the acquisition function, shown in red here, evaluation of a new point allows a new model to be built, and the search proceeds until the computational budget is exhausted. For this toy example, the figure shows the degree of exploration measured by the predictive uncertainty sigma versus the mean function. Ideally, we would like to maximize both, but there is usually a trade-off, and the optimal trade-off is captured by the Pareto set marked in red. A natural thing to do is to select the next point to be evaluated from the Pareto set, and indeed, the expected improvement and the upper confidence bound acquisition functions do so, but the probability of improvement function does not. In fact, it's straightforward to show that locations that maximize the upper confidence bound must lie in the Pareto set. Likewise, maximizing the expected improvement, another very common acquisition function, also results in locations that lie in the Pareto set. However, we show that this is not the case for the probability of improvement acquisition function or for the weighted expected improvement acquisition function. Motivated by this, we propose a new epsilon greedy acquisition function that, with probability epsilon, selects a location from the Pareto front, but most of the time chooses the most exploitative solution, that is, the mean prediction, where there is least exploration, shown in green here. We've evaluated the epsilon greedy acquisition function extensively. Here are some sample convergence plots comparing the epsilon greedy schemes with expected improvement, probability of improvement, upper confidence bound, pure exploitation, and pure exploration. Our paper gives much more extensive experimentation. The empirical results show that some exploration is desirable, but it is effective to mostly exploit the mean prediction. We suggest that this is because the surrogate model is inaccurate, which introduces inadvertent exploration, an effect that becomes more pronounced in higher dimensions. Here is an example of a 10-dimensional real-world problem of optimizing the pressure loss in a channel between the inflow and the outflow by adjusting the shape of the channel, shown as the green line. We find again that the epsilon greedy methods outperform or perform at least as well as the conventional acquisition functions, although a scheme that selects purely from the Pareto front also performs very well in this case. We've shown that not all acquisition functions select from the optimal exploration-exploitation trade-off set, and it's generally efficient to greedily exploit the surrogate's prediction because inaccuracy in the surrogate introduces inadvertent exploration. In summary, greed is good. Finally, we point out that these methods can be built on for synchronous and asynchronous batch Bayesian optimization, and more information is available in these two papers here, the epsilon shotgun algorithm and asynchronous epsilon greedy Bayesian optimization. Thank you.